All right, thank you very much for the introduction. Can I be heard properly? I guess so, right? All right, so I'm happy to be here today to talk about the Internet Computer. And let me actually start with the grand vision of this platform. So the Internet Computer should be a platform that runs efficiently any kind of computation in a decentralized manner. And in this talk, I'm going to focus on the efficient part. So it's not a talk about blockchain, it's about systems. All right, but first things first, let me just give you a bird's eye view of the Internet Computer. So we can look at it as a collection of replicated state machines. And these actually run on nodes, servers or machines or however we want to call them, which are actually placed in independent data centers. And these are actually partitioned into what we call subnets. And actually, these subnets are the replicated state machines, right? So we have many of these running on independent data centers. Now, each of these subnets or replicated state machines actually run canisters or smart contracts, another kind of terminology. So let's see. These canister smart contracts are actually what Mark mentioned a bit earlier about WebAssembly programs that can touch a lot of memory. So to give you a short introduction into how these things can actually run, our programmers can actually write programs in Rust, Python, JavaScript, and even a language that's designed specifically for the Internet Computer, which is called Motoko. And then these get compiled down to WebAssembly bytecode, which actually runs on the Internet Computer. These programs can touch up to 64 gigabytes of memory, which is quite a bit for blockchain. And these canister smart contracts can actually call each other by sending messages. And it doesn't matter if they're on the same subnet or not. And they can also make calls to the exterior through these HTTP out calls. And this is unlike what other blockchains have, which need to call oracles to talk to the exterior. All right. Now, to zoom in a little bit more, there's 4 layers, 4 systems kind of layers to the Internet Computer. So I mentioned before that these canisters talk to each other by sending messages. So the first layer there, the networking layer, is the one that's responsible for disseminating these messages. Then there's a consensus layer, which basically gathers these messages and orders them and forms blocks in the blockchain. Then these blocks go to the message routing layer, which basically takes individual messages out of the blocks and places them in the right queues of the right canisters. Then these messages are taken out of those queues and actually executed by the execution environment in a deterministic kind of way. And to zoom in even a bit more, so as I said, these canisters can actually call each other. There's 2 types of calls canisters can actually make. So there's one called update. That's kind of slow because everything has to pass through consensus. The state changes are persisted. So whatever happens in that program will stay there for later invocations. And all the computation is actually replicated. So it runs on all the machines on a subnet. Now, the opposite of that is the query kind of message, which is sort of a read-only message. So it's fast. There's no consensus. All the state changes get to be discarded. And it's non-replicated. So basically, we can have a lot of parallelism here. All the replicas in the replicated state machine in the subnet can serve queries at the same time. OK. Then what's different about the Internet Computer in comparison to other kinds of blockchains? So first of all, it has Byzantine fault tolerance. So for example, it can tolerate up to F malicious nodes out of 3f+1, so 4 out of 13, for example. Everything is geo-replicated. So at the moment, there are about 550 nodes in about 18 countries. Things are decentralized, so There are many node providers, so owners of these physical machines, and everything is self-governing. So there's no single entity that actually controls something, and there's votes that happen to apply all sorts of changes. And these changes can be additions, for example, of other nodes, or even software version changes. So if there's something that needs to change in the code, then there's a proposal, and then everybody votes in to accept it or not. Okay, now going into the meat of this presentation, as I said, it's about the efficiency part. So I'm going to talk mostly about the execution environment, and yeah, in more details about 2 of the 4 challenges that the paper presents. And the first one is statefulness, and the second one is deterministic scheduling. So let's talk about statefulness. Yeah, so basically what statefulness means is that whatever gets executed, if it touches some data, that data will stay modified for later invocations. And this is happening through what we call orthogonal persistence. So basically, these canisters or the smart contracts actually give this illusion of being forever running processes, right? And the nice thing about it is that there's basically no programmer interaction with this. So basically, you just write your program and things stay the same way. So that's an example there of a key value store canister. And it's basically as easy as just declaring a hash map variable and having 2 functions, set and get, and then the system takes care of everything. So if someone added a key value pair at some point later on for different invocations, even if there are updates or queries, that thing will be there. And that QR code over there, you can have a look at. It's basically this code that actually runs, and you can modify it and so on. Okay, now going a bit deeper into how things are running, let me tell you a bit more about how we actually achieved this statefulness. But let me give you first an overview of how things are going. So let's assume that there's a message coming in for a canister that hasn't been running for a while or at all. And as I said, we have this WASM code that programmers or users actually deploy to the system. So that's the WASM module over there. And whenever a message comes in, that WASM module is actually compiled down to a WASM binary. That WASM binary is instantiated by a WASM time virtual machine. And that virtual machine runs inside the sandbox for security and separation reasons. And it's important to mention here that the execution of the system actually happens in rounds. And every round, every canister can actually execute 1 or more messages. And every 500 rounds, the canister state is checkpointed. So basically, the memory that got modified in the WASM time virtual machine over there gets saved somewhere in a file on disk so that we can use it later. Now, going into the memory architecture, I mentioned there's a WASM time binary running under a virtual machine. I mentioned there are checkpoints. So if a canister runs after a checkpoint, actually, its memory will be basically empty. So there was no read or write. So whenever there's a fresh read, what happens is that we bring in that page from the checkpoint file. If there's a write happening, things are a bit more complex because we want to keep track of the writes. So whenever there's modifications to the canister state, we have this heap delta data structure that keeps track of all the pages that have been dirtied or modified. And for the entire checkpointing interval, we have this heap delta data structure that keeps all the things that were modified. And then at the checkpointing time, this data structure gets flattened down and actually written to the checkpoint. And things start over. Going a bit deeper, so as Mark said earlier, for performance reasons, we don't want to map all the memory at once because it might not be needed actually, right? So whenever something touches memory, we want to map those pages on demand actually. And because we need to keep track of the modifications, we have this page protection and single handler mechanism to catch all these accesses. So initially what happens is that no pages are mapped. For every read accesses, there's a page fault. We map everything as read-only, so it can be read from that point onwards. But whenever there's something written, what happens is that there's the page fault. We create this page delta data structure entry, and then we remap everything as read and write. So basically, from that point onwards, the virtual machine can actually deal with its own memory, and at the end, for the checkpointing interval, then everything gets copied to the delta and then to the checkpointing file. Okay. Yeah, so for memory optimizations, we've done quite a few. I think I'm going to pass very quickly for this graph for time reasons. So I guess the most important optimization that we've made is prefetching or pre-faulting, and that's basically quite adaptive depending on what the canister actually does. So if that reads a lot, we read a lot in advance. If that reads a little, we read a little in advance, and so on. And that improved the performance between 1.25x to 3.5x. And now let me go to actually the second challenge I want to talk about, which is quite interesting, and it's deterministic scheduling. So basically, just because we have a replicated state machine with many machines running the same thing, it really needs to be the same thing. So the same computation in the same order, and it has to have the same result. So that's one of the challenges this scheduling had to overcome. The second challenge, which is also very interesting, is charging. So like in cloud computing, when people have VMs or Lambda functions or whatever, what happens is that we keep track of time. So if something executed for 1 hour, it's charged for that 1 hour. However, in this case, if it's a replicated state machine, time is actually kind of relative for different machines, so it's not the same. So we cannot really charge based on time, because the operating system may have different states on different machines, which might make things faster or slower. The hardware might have different states, so some data center can be cooler, some can be hotter, things can start throttling, and so on. So basically, because of this, we cannot actually use time, but instead the internet computer actually uses instruction counts. So when something executes, the internet computer actually looks at how many instructions, WASM instructions, were executed, and it's basically charging based on that. There's a few other sub-challenges here, like fairness or denial of service protection. So basically, it needs to make sure that no one canister blocks the whole subnet. And something super important, because the internet computer needs to scale to larger workloads, it needs to support hundreds of thousands of canisters, or maybe even more. So it needs to have a proper scale. And we're still working on this, so it's not there yet, but yeah, it's going to happen soon. And another interesting thing that the internet computer had to do to actually make it happen. So in the context of operating system, we basically take for granted time slicing, right? So every process gets a bit of time to actually execute, right? But for the internet computer, again, because we look at instructions, not at time, this had to happen in terms of instructions. So what happens is that a given canister gets to execute a number of instructions, and then it stopped, and then we go to the other round, and so on. So why we had to do this is this figure on top. In a given round, multiple canisters are actually running. And if one of them takes longer than all the others, it's basically blocking the round. And then all the others are actually waiting, and this decreases throughput. Now, if we had this time slicing or instruction slicing, what happens is that we can keep the round shorter, we slice everything nicely, and then throughput actually goes back to what it's supposed to be. Okay, so We had serverless in the title, and this is the serverless session. So you might be wondering, is this actually serverless? So there's many definitions, I guess, for serverless. There's many things that people have to check to say that a system is serverless or not. I'm focusing here on a few things. So for serverless, developers don't need to care basically much about what happens with the machines, right? And that's also the case for the internet computer. So for the machines, just the node providers actually care, and they get them fixed and so on. Also the internet computer protocol with the installing software and all the things that are needed to keep everything running. Code is actually broken into small functions, and that's also the case here. So developers have canisters, and canisters have update and query calls, which are usually sort of short, and everything runs, most of the times well below 1 second. And then I talked earlier about billing. Basically, billing is for the internet computer at the level of instructions. So that's quite fine-grained. But there's two things that the internet computer has and other cloud providers don't have, and these are it's decentralized, first and foremost. And the second, we keep state. So that's quite interesting. So if you have workloads that need that, you can have a look here and see if it fits your needs. And if you're curious about performance, we actually ran a compute-intensive workload and compared the performance of the internet computer with one of the top 3 serverless platforms. And this is just execution times, no networking or other kinds of system overheads. And this compute-intensive workload is just computing prime numbers, so mostly number crunching. And what we can see in that graph is that for smaller problem sizes, the IC is actually faster. But when there's more work to be done, it goes to somewhere like 50% of the performance of this serverless platform. And you might be wondering why. Well, basically, it's what Mark said earlier. So the virtualization stack of these platforms is much larger. So they either have containers or virtual machines or something like that. So they just boot a Linux box with all sorts of things, code, and it's pretty complex. So for small work sizes, this is a large overhead. Whereas for the internet computer, there's this WASM time virtual machine that runs only WASM. So that can be very quick. And overall, this is quite promising for performance. People are working on improving it for the future. And going a bit deeper into the problem, like why do the overheads occur? Well, this is another workload here, and in this workload, basically, there's like this memory-intensive workload. So the canister touches lots of memory pages and computes some hash on top of them. And for all the CPU time presented here, basically half of it is just the actual workload. About 20% is the blockchain overhead, because basically that's one important part of the system, and another about 20% is just this execution environment. So with managing everything to be run, the scheduler, the memory faulting mechanisms, and so on. All right, so in the interest of time, I'm gonna go a bit quicker over this. The internet computer exists in production since May 2021, and it's been growing quite a bit since then. This graph is basically since January this year when the paper was actually submitted. In the meantime, there are more canisters with larger state. So basically at the moment, there are about 300,000 canisters with a total state size of, I think, 3.5 terabytes. And things are growing as we speak. All right, so to conclude, the IC is a blockchain platform that I think offers serverless capabilities. It's been steadily growing. The performance is good at the moment, but there's still quite a bit of room for improvement. It's been a large team effort, hence all the many authors for the article that you saw on the first slide. There's lots of systems challenges, and yeah, we like to work on them, but we invite everybody to actually give us a hand. And if you're curious about the IC, there's some links over there, and there's also this QR code that takes you to one of our pages. And yeah, if you have any questions, I'll be happy to take them now.